Good morning to all. I am Dr. M. Shanthi, Professor of Chemistry at Andhra University. So, in this video, I am going to discuss about different types of diffraction methods. Introduction: the diffraction methods measure residual lattice strain distribution in a crystalline microstructure. Diffraction patterns provide the atomic structure of molecules such as powders, small molecules or larger ordered molecules like protein crystals. It can be used to measure strains in materials under load by monitoring changes in the spacing of atomic planes. Learning objective: to know the types of crystal system, then to learn diffraction methods. Next we see the different types of crystal system and lattice types. The particles, atoms, ions or molecules in crystals are highly ordered, as is evident from their geometrical shapes, smooth surfaces and specific interfacial angles. The particles in crystals are arranged in regular patterns that extend in all directions. The overall arrangement of particles in a crystal is called crystal lattice, space lattice or simply lattice. To describe the structure of crystal, it is convenient to view it as being made up of large number of basic units. The simple basic unit of building block of crystal lattice is called the unit cell. This is illustrated in figure. It is a simple unit cell. This unit cell combine together and produce a lattice. How to represent crystal lattice and unit cell? The crystal lattice of a substance is depicted by showing the position of particles, structural unit in space. These positions are represented by bold dots or inches and are referred to as lattice points or lattice sites. The overall shape and structure of crystal system is governed by that of the unit cell of which it is composed. A unit cell has one atom or ion at each corner of lattice. Also, there may be atoms or ions in faces and interior of the cell. A cell with an interior point is called body-centered cell. A cell which does not contain any interior points known as the primitive cells. That is, a primitive cell is a regular three-dimensional unit cell with atoms or ions located at its corners only. The unit cell may be characterized by the following parameters. So, this figure shows the simple unit cells. The relative length of the edges along the three axes is indicated as A, B, C. The three angles between edges are indicated as alpha, beta and gamma. The parameters of a unit cell can be illustrated as in figure. Parameters of the 7 unit cells are listed in the following table. These are the 7 types of unit cell: primitive unit cell, cubic, tetragonal, orthorhombic, rhombohedral, hexagonal, monoclinic, triclinic. Cubic unit cell, these are the simplest unit cell. These unit cells are particularly important for two reasons. First, a number of ionic solids and metals have crystal lattices comprising cubic unit cell. Second, it is relatively easy to make calculation with these cells because in them all the sides are equal and the cell angles are all 90 degree. Next, three-dimensional unit cell. The unit cell of the three-dimensional lattice is a parallel defined by three distances A, B and C, and three angles are indicated as alpha, beta and gamma as described before. The unit cells are the basic building block of crystals. They may pack together to fill all space. The following table lists the possible unit cell shapes which are known as the 7 crystal system. Each unit cells are described by minimum symmetry requirement as detailed in the table. In the system triclinic, unit cell alpha, beta and gamma is not equal to 90 degree. Then A, B, C is not equal. The minimum symmetry requirements are none. Like this, monoclinic, orthorhombic, rhombohedral and hexagonal, tetragonal, cubic have different types of arrangement of there is a equal or non-equal of ABC or alpha, beta, gamma rays, and depends upon nature of the arrangement. Some is two-fold access, or some is some combination of threefold mutually. All these are given in the following table. Types of diffraction method. First one, X-ray diffraction, then electron diffraction and neutron diffractions. So here we discuss some basic concept of different diffraction methods. First, X-ray diffraction. Using X-ray crystallography, one can generally determine the precise composition and atomic arrangement of almost any molecule. Next, to analyze the interaction of X-rays with a crystalline solid, Bragg's law is used. The relation is n lambda equal to 2d sin theta, which can be conveniently rewritten as sin theta, that is n lambda divided by 2 into 1 by d. The expression means that if a parallel beam of X-rays fall on a set of parallel planes of crystal with an interplanar distance d, then a conservative interference of the diffracted beam will occur only for value of theta that satisfy the Bragg relationship, n being integral. Bragg noted that X-ray diffraction behaves like reflection from the planes of atoms within the crystal only at particular angle defined by theta. This figures the diffraction pattern. When a X-ray beam strikes any plane of crystal and satisfies the Bragg relation, then a single secondary beam will emerge from the crystal. In reality, in a small crystal is path in a beam of X-rays, thousands of reflections are ejected from it in various directions, and many of them being weaker in intensity, as shown in the following figure. The aim of this chapter is to present enough information regarding unit cell, X-ray diffraction, nuclear diffraction and electron diffraction methods. First, electron diffraction. The diffraction of beam of electrons by atoms or molecules used especially for determining crystal structures. If a beam of electrons are accelerated with an approximate voltage of 40,000 volts and is passed through a gaseous sample, then diffraction of electron is observed. This is so because the wavelength of electron is of the order of magnitude of internuclear distance in molecules. By de Broglie equation, the wavelength of electron is lambda equal to h by mv. M is the mass of the electron, h is Planck's constant, v is velocity. Electron accelerated through a potential difference v will have a kinetic energy given by the following equation: mv square divided by 2 equal to ev, whereas E is the electronic charge. From the two equation eliminating V, lambda can be obtained as lambda equal to h by mv into mv divided by 2 ev whole squared square root, lambda equal to h by 2 me and ev root square. For an applied voltage of 40 kilovolt, an approximate value of wavelength is 0.06 Armstrong. Since electrons have the low penetrating power, electron diffraction is mainly used for the study of gases. Neutron diffraction. Neutron diffraction or elastic neutron scattering is the applications of neutron scattering to the determination of atomic and magnetic structure of the material. A sample to be examined is placed in a beam of thermal or cold neutrons to obtain a diffraction pattern that provides information of the structure of the material. This technique is similar to X-ray diffraction, but due to their diffraction scattering properties, neutrons and X-rays provide complementary information. X-rays are suited for superficial analysis. Strong X-ray from synchrotron radiations are suitable for shallow depth or thin specimens, while neutrons having high penetration depth are suited for bulk sample. Sources: the neutrons are released during atomic fission and hence are highly energetic with high velocity and small wavelength. In order the wavelength to be in the order of 1.0 Armstrong, velocity of the neutrons must be slowed down by collision with atoms. At a given temperature T, the neutrons will have root mean square velocity v given by the following relationship. Here mv squared equal to divided by 2 equal to 3 kt, then root square. Here mn is the mass of the neutron. Substituting value for v from de Broglie equation, v equal to h by m lambda. then lambda square equal to h square 3m kt. At t equal to 0 degree, a neutron wavelength is 1.55 Armstrong, and at t equal to 100 degree, the wavelength is 1.33 Armstrong. Therefore, the range of wavelength is 1.5 Armstrong, which is convenient enough for diffraction process. In order to have a monochromatic film, the emerging neutrons from an atomic pile are diffracted from 220 planes of calcium crystal with a wavelength of 1.16 Armstrong. However, the monochromated beam will actually be small band of wavelengths, since there is nothing that corresponds to characterized radiation of X-rays. A beam of neutron is weak compared to beam of X-ray from any source. Therefore, the beam of neutrons have to be broader enough to have comparable and detectable diffraction effect as those of X-rays. This also requires a larger crystal or simple sample in a general for neutron diffractions compared to X-ray diffraction. Scattering of neutron by solids and liquids. Generally, a neutron scattering reaction occurs when a target nucleus emits a single neutron after neutron-nucleus interaction. There is no energy transfer into nuclear excitation in an elastic scattering reaction between neutron and target nucleus. The elastic scattering conserves both momentum and kinetic energy of the system. This is usually some transfer of kinetic energy from the incident neutron to the target nucleus, either solid or liquids. Target nucleus gains exact amount of kinetic energy that the neutron lost. The interaction can occur via compound nucleus formation, but in the case of elastic scattering, a neutron emission returns the compound nucleus to the ground state of original nucleus. Compound nucleus is an unstable nucleus formed by the collision of atomic nucleus with captured particles. The elastic scattering can occur by way of two interaction mechanisms: potential scattering, compound elastic scattering. Potential scattering. In potential scattering, the neutron and the nucleus interact without neutron absorption. In fact, the incident neutron does not necessarily have touched the nucleus, and the neutron is scattered by the short-range nuclear forces when it approaches close enough to the nucleus. Potential scattering occurs with incident neutron that have an energy of up to about 1 mega electron volt. Next one, compound elastic scattering. In some cases, if the kinetic energy of incident neutron just to right to form resonance, the neutron may be absorbed and a compound nucleus may be formed. This interaction is more unusual and is also known as resonance elastic scattering. Due to the formation of the compound nucleus, the initial and final neutron are not the same. So, in this video, we discuss types of, there is a crystal natures and different types of diffraction, X-ray, electron and neutron diffraction, their concept. Thank you.